show you correctly. So this is the Markov chain. How many states here? In the last row, we have 1024 states. And in the first one, we have 32 states. So in total, there are around 2000 states in the Markov chain. And we can actually analyze the performance of the mechanism within this impact Markov chain. So we'll see in the next class. And now, so our objective is to learn how can we actually use Markov chain to analyze the performance of any system. We can consider a protocol here as a system, and we will develop a model, then we will solve the model to get a corresponding solution, and eventually we can analyze it. A question actually we discussed in the last class. In the model, we consider that a pure ALMA system is modeled into three states. So what are these states? State 0, no expression is transmitted, 0 or 1. Okay. State 1, only one expression is transmitted. So in that case, we can consider the expression is going on. And state 2, where 2 or more expressions are transmitted together, we call it collision. Right? Now, if this is the tangential probability graph, when the system is in idle state, it remains idle with the probability U0. What UK is the probability that any solutions are transmitted. And so, when k is equal to 0, this indicates none of these solutions are transmitted. With the probability E1, we move from state 0 to state 1, we say only one solution is transmitting and it's successful. And if none of these two occur, that means the network is not idle, not a single station is transmitting, that means two or more stations are transmitting simultaneously. And so, that occurs with the probability 1 minus U0 minus and the collision state is the next. When the Markov chain is in transmitting state, that means one station is transmitting, then we have two scenarios to consider. The transmission is successful without any intervention from other stations. So we have a time where actually no stations is transmitted, and that occurs with a probability E0. Or when the single station is transmitted, these stations are pretty much careless about the situations of the other stations. Even though single station is transmitting and single bit is remaining, any station can be selected. So from there, the next step will be a collision state, and that occurs with the probability 1 minus E0. Note to me, this E0 and this E0 are not exact. There is a clearly but following the text we consider they are identical. Now, when the network or the chain is in state 2, then what happens? Collision can eventually be fixed, and none of the station is transmitting. We can move forward here with the probability. From a collision state, we cannot move on to the transmitting state because to be in the transmitting state, the network should be idle. That's why we have a collision. We can be in a collision state with the probability of plus. Collision can happen in long before the collision actually is cleared, another station can start transmission, then another station. That's why actually the maximum throughput of an alpha network can achieve when there is only half rate alignment in different transmissions. When half rate arrives, can on an average, only there is the maximum efficiency and that is only 18%. 80% of the median times are either kept idle or actually wasted due to explosions. And out of it is to calculate this thing how we can get that 80% of the time actually the median is used effectively and remaining 80% of the time either there are conditions or there are idle. Since the packet arrival rate should be very low, a chance exists that a large portion of the time the network is no one is transmitted. Another portion of the times many stations or at least two stations are transmitted simultaneously. And so both of these two actually result in no utilization. So the period of time is that only when the single system is transmitted. Now from this one, what we can have an opportunity represented by the television special I here. From the idle state, you can move on to idle state with probability not. From the position state, you can only probability 1 minus 1 minus 1. And the successful transmission state from this one, it is 1 to 3. And so on, right? So we can have the non-time condition probability defined is according to this notation. We have 3 S's, y1, y2, and y3, with non-time probability equals this one. Then we can set up a system of linear equations by some. I will show you how to solve some simple system of linear equations by solving the system of linear equation. So this one actually is the idle state. This one is the position state. And this one is by the term transmission will be the probability that a single section is transmitted to frame okay. And so this actually is the starting. So we have a closed form solution here by modeling the system using a discrete time alpha chain with these 3 steps we develop the condition probability graph, and from here we assume that this is the long time probability vector and solving the system of linear equation we will get it. And once we are here, so now we will measure the particles. Remaining particles will just solve. What is this? First one is throughput is defined following the test. As the fraction of time the medium is used or the network is used by serials. What is the fraction of time? Actually, this pi 3 you use this. So as considered the steady state probability vector, we mentioned that probably equals pi and pi 1, pi 2, pi 3 are the steady state probability for a state 1 and so on. We actually use this. This is the steady state probability vector and probability for a state 1, 2 and state n. So pi and s are same variables, so we will be using it. So this is the throughput. And now we know the value of U0. U0 is 1 minus n to the power n. U1 is n times a times 1 minus n to the power n minus 1. So putting this, we will already have this values. And putting this value together, what we have n times a times 1 minus n to the power n plus n minus 1, which is actually very less. That's what we have. And some approximation, there is a formula. You will find it later. We can approximate this term to something like 1 minus x by n to the power n equals to the power minus 1.
What is small a?
The equivalent to it. Right?
What is small a?
It's more then we call it A is the probability that A station has a friend who transmits. Or you can consider the probability of arriving a friend to a single station, right? So that means how many stations are here? We have number of stations. Then these probabilities that we have, so what is being brought? We discussed this in the last one. Among the 8 stations, none of these stations is transmitted. What
ভাই
is the probability
সুইচ
that
অফ
a
করে
single
দেবো
station is not
শাহিন
transmitted?
সুইচ অফ করে দিতেছে
1 minus A. What is the probability that A station is not transmitted? 1 minus A times 1 minus A times 1 minus A. How many? What is B1? Probability that single station is transmitted. And following the binary distribution, it is N choose 1, which is N. Then A to the power 1, which is A. Then 1 minus A to the power. Right? So these two are the variables here. Now, this throughput actually is measured in the scale of time. The fraction of time that is used for successfully transmitting frame. You can actually measure the throughput in terms of frame per second. When you do that, actually we mention what is the length of it. And if we divide the throughput by the time, then we actually get the throughput in terms of frames per second. Just chance. And for sloped alpha, this one, and this one is the for pure alpha, is the throughput. When we change the input traffic, which we define as NA here, like this. Okay, you can see it clearly. Or by changing the A, that means the arrival rate in the probability that the friend is available at a station is A. If you reduce the value of A, that means probability is increased that the station is available to transmit. If A is 1, that means almost all the times a station will have a friend, and that will result in a pollution all the time. You are all just false. Right? On the other hand, when A is very less, then a station has a friend will be with a very less probability. And all, let's say, among the N stations, there is a friend that probability will also be less. Now, what is the total traffic? Network traffic. Or if that's a network load. Probability that a station has a friend is A, N station has a friend is the probability that we will go there later. Now, as we increase this one from 0, the network level is 0, there is no friend, throughput will be 0. As we increase the network load, throughput will be increased. And we will reach the maximum point. After that, the collision rate will increase. Even though we increase the network load, throughput will decrease. And eventually, the throughput will be even higher. Okay? So, this is just a graph. Now, how can we find a graph like this? The input traffic or the network load in the traffic is NAE, is defined that a single station has a magnetic probability A, and there are 8 stations. Total loading of the network will be N times A. So they are these. Now, what is the probability that it is successful? That is defined as the efficiency or acceptance probability. What is the fraction of the estimator of access or our successful? This is found by this equation. What is this? Throughput is the fraction of time the network is used, fraction of packets that is used successfully, transmitted successfully, and N sub A is the total number of packets that arrive into this. So this fraction is giving you the probability probability of success of it. Okay? And by putting the value of case here, you put that earlier calculated and approximated, you get this. And this is the equation where n tends to infinity is 1 minus x the n becomes e to the power n square by 3. Now, what is the average number of attempts before a successful transmission? What does it mean? When a station will packet, it will transfer. And the station will eventually get the result, either it is successful or failure. What happens after that? The station will be transmitted. If the station immediately retransmits, what will happen? Since this packet was lost due to a collision, that means two stations at least were trying to forward the transmission. So if they start the transmission again, then what will happen? The collision is always. That's why what pure alpha assumes is A is the probability of transmission. Now, when a frame is lost, lost or actually corrupted, what happens? Two conditions actually are assumed. One is at any moment a station can have only one frame. So the result somehow is actually designed in such a way until the frame is forwarded successfully, this station will not be another. Second thing is that after a collision, the frame is retransmitted. With probability. What is it? At any particular time period, a station always have the probability A to transmit. If the station is idle, then it receives a packet with probability A. If the station experiences a collision, it forward that same packet with the probability A. So whatever happens, whether the station is going to receive a packet or whether a station is retransmitting a packet, in both cases, the probability is A that the station will transmit a packet at any point of time. Is this clear? Now question is, second, what is the average number of attempts before a successful transmission? Is that issue? Whenever a station actually is receiving a packet, it immediately transmits. If a collision is there, then actually it waits a random amount of time, same packet transmission time. Then after that it transmits the same packet, it transmits with the probability A. And the success occurs with the probability what? B. That a frame is successfully transmitted. Now, what is the average number of attempts before the successful transmission? Meaning, what is the average number of failure, right? What is the average number of failures before a successful transmission? Let's say the average number of failures before a successful transmission is X. X, let's say Y. So what is the distribution of the You said it's geometry. Okay, it is geometry. What is the parameter? When you toss a coin, the probability gain is the parameter. That is probability of success. We have probability successes. These are right. Now, if I write the PNF of Y, what is the is this already? What? Here is actually problem. A conventional geometric identity of X represents number of atoms till the first success. The random variable y that we have considered here is considering number of atoms until two random variables are geometric. They have the same nature, but the number, the value that x represents, x, the set of values for x is 1, 2, because number of atoms till the first success at least requires 1 atom. Unless it does required, you cannot get it. On the other hand, the random variable y that we have considered here actually have the set of possible values 0. In the best case, a packet can be transmitted, a head can be obtained without getting or without getting it. Is this clear? So, accordingly, the PMF of x that you already know is P times 1 minus P to the power x minus 1, x is greater than equal to 1 is the distribution. But for y, actually, we need to remove this part. The PMF is PA times 1 minus PA to y. Because we are not considering the attempt that actually is used for the success. We are counting before that one. So, y actually is equal to x minus 1. And it becomes a system. So, when x is 1, what is the value of y? Y actually you need one attempt to hit, then y actually is 0. You get 0 name before it. When x is equal to 2, that means you need 2 attempts to get a head. One tail followed by a head, then y is equal to 1 because the number of tail before head is, first head is 1. You understand this one, right? And that's why the PMF here is and the expected value. The average number of atoms, the expected value actually is, you know the formula for expected value is x times PMF of x for the value of x. Here actually x actually is n, and for y it starts from 0, it goes up to infinity, and the PMF is 1 minus PA to n times PA. We understand? No, probability is that actually you have the success there. The random variable x and y are actually probabilistically same. When we are, okay, this is a very good question. When we are considering that 1 minus PA, it is telling you that you have y successive values. And the path is here. It is not guaranteed that the next one was a success. But when we are mentioning this probability says not only y failures are there, which was followed by a success. And it guarantees that you exactly have actually y failures before you transmitted the failure. When you write this is the probability, this says that you have y consecutive failures. It does not guarantee. The packet is transmitted. You got it? That's why the probabilities are identical, but according to this relation, we have, okay, since we are considering that y failures are there, probability is this one and the success is there. And we are considering that the random variable y goes from 0 to something, and this one goes from 1 to something. Anyway, now the expected value actually is, what is the expected value for a x here? We know that, right? 1 by, due to this relation, y is equal to x minus a. What is the expected value of y? We know expectation for some of random variables are some of their indivisible. So it will be expected value of x, which is 1 over b. Expected value of the constant is the constant. So this actually is 1 minus b divided by. So this random variable, derived random variable y, has expected value 1 minus b a minus b a. Whereas the geometric random variable, the conventional one, has expected value which is 1 over b. That's why we have 1 minus b a divided by a. Okay? And now, we come back here. Say you attempt here the success. Eventually, you got the success here. So this one was the failure. This one was the failure. So average duration before actually you get the success is just the value of any number of failures and the average duration of failure. Average duration of failure is not fixed. Whenever there is a collision, the collision can lead to a length of this one. Even successive collisions could lead to this further. Even due to successive collision, you might have an idle period. So calculation of this one is, and the issue will not be. Following the text, we will just say, if we assume that actually whole length is tau, then the total working calculation is. Finally, what will be the maximum throughput of the system? As we know, the throughput is a function of what? Throughput is a function of A. Here n actually are constant. So if we differentiate it with respect to A and set it to 0, then we will find the value of A for which the throughput is maximum. And following the test, this is the value of A, we define it as A naught, for which the pure error system has maximum possible throughput. And the maximum throughput by putting this value of A naught in the equation, we get this one, and we simplify it as this one, and eventually this is one. So pure alpha sees a throughput of 18.4%. This is the maximum possible. So in 1 second of time, 18% of the time is transferred successful brackets, remaining 18%, or any say 1%, 1.5 or 6, either this can be between inside and actually collisions are there. And this occurs when the network node actually is 0.5. That is not shown here, I guess. The network node is 0.5 and for alpha when it is 1. That means on an average in one packet is they are in the packet. The network has the highest control. So, any question here? Now, we move on to slotted alpha. Slotted alpha system, how actually the protocol is designed. Stations are synced, not synchronized. By the term synchronized, that means they have the same code. This is very difficult. You know how nowadays actually we achieve synchronization? We have a server that maintains the code. Each of the station requests every time. and server actually provide the time to this expression. And we usually calculate the time based on the delay. It estimates the delay of sending the request and getting the feedback, and then based on that restriction actually calculates the time. And by showing every single restriction in data, for example in IoT, every single network needs that answer, especially the IP cameras. And the IP cameras, based on that, actually the IP camera shows the time. That is now become very important. Every single day we receive at least one request. Something has been stolen from the observation. And in response to your question, actually one of our CSE department student lost his laptop. So, the stations are synchronized and they have the same time and the transmission boundaries are defined. You can start a transmission only at that. If you have a friend arrived on or before this time, only then this section can start. If the time is passed, then you cannot start. So if a collision is there, then the collision can occur from simultaneous. If a station can start the transmission alone, then the transmission will be successful. Unless there is a channel error, and channel error is required even deliver beats only one bit can be done. Whereas the general say packet size is 500 to 800 bytes. So it is very low. So a packet can be transmitted only at the start of it. So now once again, a slow time actually is already defined. A station can start a transmission at the beginning of the slot, or it is two-way. If two or more stations have packets, arrive packets in a single slot, then this will lead to a collision, and once again after a collision, a station will randomly choose. So, like before, A is the probability of getting a packet, and after collision, it will transmit the packet. It has the packet, but it will transmit the packet with the probability A. So, India's calculation will be that. Now, the question is, the network can be once again in three different states: idle, collision, and transmission. The question is, what are the probabilities? From 1, 2, 3. So, what are the probabilities now? Well, I will finish it in 1 or 2 minutes. So, before that, you have the time. What are the probabilities that when you can get these idle state, 1 is stand for idle, 2 is stand for collision, 3 is stand for. So, if you actually complete the probability transmission, state transmission, probability transmission graph, or matrix probability transmission graph, then these are the nodes of the graph. And now we need to show the edges and put the edges. So, when the station is in state 1, that means when the network is in idle state, we will be idle in the next slot. So, at the beginning, it is idle. What is the probability that it will be idle at the beginning of the next slot? Why? If no packets arrive in any of the n stations, and that occurs with the probability what? You have to go through. No packets arrive. So, given current state is idle, the next state will be idle. The next the beginning of the next slot, current slot is idle, but the probability that at the beginning of the next slot to get the idle is you not and will not be the probability. So if it is currently in step 1, what is the probability that it will go to step 2? Transmitting step. And that occurs with the probability if the nonlinear supply station. And once again, U1 is the same, n, a, 1 minus a, n minus 1. And it moves on to the collision step. If 2 or more station transmits, that can be calculated. Right? Now, if the current state is transmitting, then until the slope ends, it will remain in the transmission state, because in the middle of the slot, a station, any station is not allowed to initiate the transmission. So we can assume that transmission will be successful. Then we have two possibilities. In the next slot, either no station is transmitting, so we go back to state 0, 1, or we remain in state 2 with the probability 1, or we go to step 2 with the probability. So when we are in step 3, the transmission step, in the next slot, we can have all three possibilities. That will be fairly successfully transmitted. So in the only one frame arrives here, a transmission will be probability 1, no frame arrives, so it goes back to idle state. 2 or more frame arrives during the transmission of this period, so a collision is there. Now when we are in state 2, we can have three choices like before. One is U0, U1, 1 minus. So we understand it. And in the book, I guess you have the book downloaded. Actually, you can copy paste error. The neural model figure has been actually printed. So the corrected graph will be like this. And we will have a transition probability matrix like this, and we will not write it like that. Right? As I mentioned in the last class, what the book does, is P11, it is P21, and it is P81. But what we prefer as let's say this is P1. We prefer is P11, P12, P1. So P actually that we use is the transpose of P1 or transpose. Okay? The question is, what is now for this probability transition matrix, if pi is the steady state probabilities, can anyone tell what are the values of pi 1, pi 2, and pi 3 just by seeing the matrix? 1 by 3, 1 by 2. Who goes for 1 by 3? Who else? Raise your hand. 1 by 3, actually, we mentioned that when the matrix is double is stochastic. And double is stochastic is defined as what? Both rows and columns are summed to. Is it possible that to be this one, U0 and U1 should be exactly equal to this many of this, right? So when you increase the value of A, the probabilities will increase. Now, what is pi? Pi is the steady state probability, right? Can anyone see another properties of pi? Say the N-step transition probability. N-step probability, if you currently in step 1, what is the probability that you will be a step, say I, after N transition, right? The pi says that the N-step transition probability for N being very large does not depend on its starting state. So for all steps, the probability will be identical. That means we no longer need a metric, rather a matrix. When all the rows in the matrix are identical, in that case actually we no longer need a matrix. If we actually look at this matrix, the rows are, it is already and for this what will happen? This S1, S2, S3 will be simply S1 will be this one, S2 will be this one, S3 will be like this one. You can solve it by this way. I can already solve it. Then I realize that it is already solved. So the probability that successful transmission occurs now is 1. It doesn't make sense. Because in a slot, if a single frame arrives, then in the next slot, the transmission will be successful. So this is the probability for successful transmission. And based on that, what we can do, we can calculate very similar things, right? That we did earlier. And this one, all of these are very close, just ends are different. And eventually, the maximum total occurs when A of A has the value 1. Right? That means, what does it mean? It's 1 over N and 1 over N. It says that what is the probability? It says that the maximum throughput occurs when, on an average, there will be a single frame to transmit in any sections. And the single frame will be successfully transmitted. This one says, on an average, there will be half frame. Right? In a frame transmission frame, there will be half frame. And due to these two, actually the efficiency is 18.4 and the efficiency is 769. Right? Questions? Now we have the CS and the CD. Before we move on to the CS and the CD, do you have any questions? These protocols can be actually changed into many different ways. You can see the last year question. That's what was it? Is say the pure aroma has been checked. In such a way, when transmission is successful, the expression has to transmit the same. How will no, that one is for CSNA. That was for CSNA. That was for CSNA. CSNA actually when a station finds can be free transmission. If it finds the transmission is successful, it assumes that no other transmitted. So the transmitted station actually goes for back-to-back transmission. How that will affect the performance of the program? Instead of sending a single packet, now you will transmit one more packet to the idea or this. Now you can change it. With P probability, if the first one is successful, then you send the second packet. 1 minus P probability, you do not set a second. Anyway, let's first study the CSMCD. At the beginning, I already explained CSMCD, right? Listen before. God. That is exactly what CSMCD stands for. Before you start talking, listen whether anyone else is talking around me or not. If you find no one is talking, then you start. What is the problem? Two persons actually are attempting to talk together, then they will sense the neighborhood or the space, and they will find no one is talking. You can start talking together. Any connection is there. Since when you are actually talking, if you keep listening, keep listening when you are talking, then what will happen? If two or more people actually are talking together, then what you are telling, you will not be hearing the same. Because your statements already have all that. But you are talking, you are not hearing that much. So, if you hear the same thing, no solution. Different. So the protocol is so simple, right? Anyone can actually develop such a protocol. The person who has developed actually CSMC should be given a Nobel Prize. Because whatever internet we are currently enjoying, that actually started with a very big success of this. Earlier days, the aim of developing or designing any protocol was to make the protocol as simple as it is. And the best example is the IP protocol. The whole world is still scaled by this IP protocol. You can see the IP has now evolved a lot. There are many protocols under the IP. There are many protocols above IP. But you know what? Even IPv6 has been a different version, not a different protocol, has been actually tried for the last 3 decades, I guess. As I am actually following for the last 3 decades, IPv6 has been actually tried, but still we are using IPv6. And you know, IPv6 the main thing is very simple. When you are as correct as possible, transmit the packet as maximum as you can. No guarantee is there. That's why IP is called distributed service. So when you deliver, make your reflect as mass as you can. And when you receive a packet, before discarding it, try your level best as no guarantee. Multiple device. So the earlier eight actually the main thing was to design protocols using CPC. But nowadays technology has changed. All machines are there, computers are there, AI technologies are there. Even you can start systems like semantic communication. Previously, we assumed that the sender and receivers actually are dumb in process. They have actually zeros and ones. They transmit. The receiver just receives zeros and ones. Now we assume that they are in example. We have a teacher sending something. We have actually a student receiving something. While sending the data, teacher actually is teaching the receiver what it is saying. And actually, by this way, you don't need to send something in the amount of data. For example, you are sending 2 images. Only the position of a flower has been changed. In the second image, you don't need to change the whole image. You can just send the data. So that's how actually the communication has been changing. Anyway, will finish with the difference between the CD and CD. Who can get it? The difference between this section and one, right? How we get it? The difference between CD, the CD actually has the prefix CSM. This CA has the prefix. So tell me the difference, I'll finish. By this time, let me
attendance can sheet this up. The person attendance could buy his time.
you may ask activity by this time.
You can choose पर मार देंगे
If you want to,
बोलो करो
so do you know what?
Yes, sir.
Please respond. 4, 5,
Yes, sir.
6,
Yes, sir.
7, 8,
Yes, sir.